to Ishan Misra, our keynote speaker. Have you seen it? Who? Ishan Misra.
I don't know. That's personal.
I hope he will come.
I think if someone don't come, just move to the next one. Just change it over. Right?
Okay.
Okay, we can start. So, hi everyone, and welcome to the 6th edition of our workshop, AI for Creative Visual Content Generation, Editing and Understanding. I am Ozgur from UIUC, and I will be giving the opening remarks before we begin our program. So let's begin. I would like to begin opening remarks with a quote from Marshall McLuhan, who once said, "We become what we behold, we shape our tools, and thereafter our tools shape us." So this quote correlates deeply with the work that we have been doing today in our research. As we build generative AI systems, we are not just redefining how content is created, but we are also reshaping how creators think, how they express things, and how they imagine. So inspired by this idea, today's workshop is dedicated to exploring the future of generative AI research and the practical challenges of these models that we face in our real-world applications. So if we come to the goal of the workshop, we aim to foster a cross-disciplinary community united by a common interest of advancing the technology for creative, video-centric generative AI. To achieve this, we have been actively connecting experts from diverse backgrounds, spanning computer vision, machine perception, generation, as well as some independent artists. For example, a recent effort that was organized by Anye Rao, the first Hong Kong University of Science and Technology AI Film Festival, continued this effort to bring the community together. So today, in this workshop, we will be holding 6 keynotes, 6 keynote presentations. We will have 2 sessions, and in each session we will be having 3 keynote presentations, 1 roundtable discussions, and in between the sessions we will be holding a poster session as well as an industry session. So this is our detailed schedule. So we will first start with future of generative AI research topic in the first session, where we will have Ishan Misra as our first keynote speaker, who is from Meta, and will be talking about foundational models for video generation, editing, and personalization. Then we have Dan B. Goldman from Lucasfilm, who will be talking about reinventing movies again. After, we will have Eli Sheikman from Adobe, and his presentation will be about towards interactive video generation. Then we will be doing a roundtable discussion where we will have 2 additional guests, Krishna Kumar Singh from Adobe and Ming Shan Yang from Google DeepMind. After we finish the roundtable discussion of the first session, we will continue with the industry and poster sessions, which will be held between 3 p.m. to 3:45 p.m., where we will have some demo sessions from Fall AI and Abaca AI. After that, we will continue our second round, second session, where we will discuss challenges of generative models in practice. And as our first keynote speaker in that session, Joel Simon will be giving a talk who is a developer in ArtBreeder, and his talk will be about directions for Humani ML creative tools. Then we have Matthias Niesner from Technical University of Munich, and his talk will be centered around 3D generative AI. Finally, at the end of the keynote speakers, we have as the last speaker Nathaniel Ruiz from Google, and we'll be talking about generative infinite games toward unbounded interactive worlds. After the keynote presentations, we have a second round of roundtable discussion where we have Dutran as an additional guest from Google. So before beginning the program, I would like to give a remark on the increasing trend of paper submission to our workshop series. So this is the 6th edition of this workshop series, and the series started on ICCV 2021. And in that, at that time, we had only 14 submissions that are both in proceedings and excellent abstracts. And currently, this year, it has reached up to 46 submissions, and it shows that there's an increasing interest and attention to both of our workshop and to the field that we have been working on. We also have a large team of program committee from different countries, different continents in the world who helped us review the papers. So these folks are from Asia, Europe, Middle East, North America, South America, and let us thank them for their great services and diligent work. We also, it hasn't finished yet. We also want to thank to our sponsors, Fall AI and Abaca AI, for supporting our workshop this year, and their generous support made this community to get larger and larger, and they help us in getting bigger. And yeah, welcome again everybody on behalf of all the organizers. We are organizers from different backgrounds, from different universities, companies, and even different seniority levels. So this is the end of my presentation, and we will then begin with a presentation from Ishan Misra when he arrives. Okay, yeah, he's just coming. Yeah, thank you again. I hope you enjoy.
Thanks for having me. Today I'll be talking primarily about video editing and personalization models. This is part of a project that we did at Meta called MovieGen. And so MovieGen basically started out as a very foundational text-to-video model. The idea was basically that given a particular text prompt as input, we wanted to generate videos as output. So this was just project really trying to figure out how much could we push video generation. And the thinking behind this is basically the more capable your foundational model for text-to-video becomes, the more easy it is for us to sort of extend it to do other applications like editing and personalization. And that's sort of really what I try to focus on in this talk today, which are not really the text-to-video applications of MovieGen, but really the editing and the personalization aspects of MovieGen. And so the other reasons, of course, for doing this, apart from creativity, are really the fact that these models essentially become very good tools for unrolling plausible futures and really like simulating a lot of things happening in environments. And so just to give you a sense for the quality, this is basically what the pixels generated from the model look like. These are all like HD quality happening at native frame rate. And so when we launched MovieGen, we launched it across like 3 things, which is basically MovieGen Video, which is a model that can do text to video performance. MovieGen Video Edit, it's a model that can do editing of videos, so you can actually edit videos in free form. And then MovieGen Personalization, which can basically take faces and basically put them into videos. And so these are 3 things that we basically release along with MovieGen. And the key way of doing this is basically, in terms of pipeline, is that we actually train the text-to-video model, which is the foundation model first, and then we perform extensive sort of post-training to get it to do like high-quality text-to-video or personalization or editing. And the task of personalization, basically, to give you an example, is that you start with a person's face. So this case is Animesh, who's one of the authors of the paper. And we now have a text prompt basically saying, imagine this person sitting in the desert with a glass of wine. And so now what you have is basically the model taking this person and putting them into this particular video and sort of maintaining a lot of consistency around faces. For video editing, we focus on this task of preciseness, where the idea basically is, and free-form instructions, where the idea is that given an original video, you can actually type out what you want in terms of the edits in free-form text, and then you'll end up getting the edited video. So the model is exactly following the instructions of the user and performing the minimum edits needed to basically obey the instructions. So it's keeping most of the video the same. I'll quickly touch over the key sort of improvements that enable this type of performance before going into post-training. So the key things that basically we changed from our prior work into MovieGen was basically that we ended up drastically simplifying the architecture and training objective. And this was a very significant departure from the way we trained these models before, both in terms of like how, what the architectural blocks look like. We actually ended up essentially moving to the Llama style transformer models for training these diffusion models, and we also ended up shifting the training objective. This massively changed the scale and the type of the results that we were getting from our model. This also allowed us to scale up the model by essentially an order of magnitude across the model parameters, the compute that would actually be needed to train the model, and the data that it used for training. And finally, of course, we spent an extensive amount of time on improving the training data quality. So I'll just touch on one thing which I think is pretty useful for people training these models, is the training objective. So flow matching, you've probably heard a lot about this thing popping up more and more compared to diffusion. And there's a very strong reason. I think many papers now are finding that this is working out very, very well for them for flow matching versus diffusion. And the key idea for flow matching is basically that it actually simplifies a whole lot what's happening inside the complex diffusion process. The idea now becomes that you have an original video, you have a Gaussian noise, you linearly interpolate between these two things to create your training sample, and then you're asking the model to make a fixed prediction, which is basically the difference between the original video and the noise video. So it's a very simple process in terms of what you end up doing. In terms of implementation, it's about 50 or 60 lines of code. It's simple to implement and actually performs super well. So we ran initial studies when we were training MovieGen, essentially comparing flow matching to diffusion, controlling for the model parameters, the training flops, and the training data. And we found that in a head-to-head comparison, flow matching almost always yielded better models, so 20 points in quality, while actually converging much faster. So you could actually train these models and sort of for the same amount of compute budget get much better results. The other finding that was actually pretty critical is that typically in the LLM world, perplexity is actually very nicely correlated with what the model's performance is going to be at the end. And we didn't have that side of proxy for these large-scale diffusion models. Human evaluations are not always feasible. And so what we found is with flow matching, for the first time, validation losses actually correlated very well with human judgment. And so this actually enters up an entire new paradigm, because now for model development, if you can actually trust your validation loss as a proxy for your architectural design changes, ablation studies, this actually makes a huge difference to how quickly you can iterate over models. And second, it actually helped us to establish scaling laws really well, because we could use these validation losses to establish precise data and model scaling laws. And so this was a pretty big deal for us in terms of how we use these models. The second finding was that actually we could have faster inference without doing any distillation. And so this really came down from the fact that what an empirical observation of flow matching, that basically on the left hand side I'm plotting the change in the activation with the model as a function of its inference time steps. And what you find is basically the model's biggest change in the activation actually happens towards the earlier part of this time steps rather than towards the later part. What this means is that in practice, when doing inference, you can actually sample much more close, like finely, the inference time steps towards the beginning, and much more closely the inference time steps towards the end. And so just by like doing this like test time trick, you can actually get very fast inference. And so we ran basically like human evaluations for this. We found that we can actually get the same quality of generation with 50 inference steps that we were actually getting with 1,000 inference steps linearly. So it's almost like a 20 times speed up for free just by doing this. And of course, this is completely orthogonal to like distillation or other types of tricks that you can add of course, later on. So this was a pretty neat finding. All right. So in this talk, again, the focus is basically on this edit and personalization piece, which is how did we enable, like go from this text to video model to enable it to do editing and personalization. So the task of video editing is basically very roughly formulated as going from text plus video to video. So it's a video to video task. And we really wanted to focus on precise editing. And what I mean by that is that when you give an instruction, the model should very strictly follow that instruction and only change the pixels that are needed to obey that instruction. So here are two examples. You have an input video, and we use the same instruction, which is add a red cape to the man. We give basically that instruction to the runway model and to our model. And what we observe is there is a lot more changes happening in the input video from when you look at the output produced by the runway model. So it's changed basically the scene lighting. It's also changed a lot more things about the person rather than just adding a cape. And so this is not really, it's a believable edit because the video actually looks good, but it's not a precise edit because it's not really followed my instruction to what I wanted it to do. And so on the right hand side basically is what MovieGen ends up giving, which is a precise edit. It keeps everything about the input video, the structure of the input video the same, except the fact that you asked for a cape. And the big sort of challenge for doing video editing is basically the scale of data that you get for video editing versus text to video is like almost 2 to 3 orders of magnitude different. For text to video, it's very easy to scale up data. You can actually get a whole lot of video and text pairs, even generate text synthetically, and you basically get a very large training corpus. For video editing, this is not the case. You don't really have precise video edit pairs available at scale, and this is a huge challenge when training these models. The second difference basically from text to video is the fact that you actually have stronger visual conditioning, because you actually have real pixels that are provided to the model, and the model needs to just edit those up. So it's a lot sort of, it's a lot more, there's a lot less information filling that the model needs to do because it actually has access to ground truth pixels. And so as a consequence of both of these things, we actually decided that video editing will basically become a post-training capability for us, where because of like we don't even have that much data, and the fact that it's actually a stronger condition problem, we can maybe just look at it as a post-training capability. So the architecture for video editing is quite straightforward. You take your input video, and you convert it from the pixel space to the latent space. You take your target video, you convert that also from the pixel space to the latent space. You noise the target video, and then you basically concatenate, patchify these things together and feed them to a diffusion model. The diffusion model also gets basically the instruction, which is like make this particular video brighter. And now basically it will just iteratively denoise the target until it gets the target video. So it's a pretty simple like architecture. The main sort of innovation really comes down on how this is being trained because we don't have a whole lot of training data. The training recipe for video editing follows these like multiple stages. So the first stage is basically text to video training, which is of course the foundational capability. The second stage is actually something that we found is we experimented with, and we were actually quite surprised at how well it worked. So the idea here was to basically just do multitask learning. You do image editing and text to video generation, and then at inference you feed the model a video and then you look at what happens. And what we found is actually the model does do a pretty reasonable job at video editing already. So without ever being conditioned on the video input, the model actually learns to combine this image editing and text to video generation capability and actually do video editing. So now basically once we started noticing this, we also found a few more things we could improve. So the next two stages are really designed to sort of really enhance this video editing capability. The next stage is multi-frame, where we basically end up synthesizing a lot more data, also add recognition tasks with segmentation, for example, that really sort of enhances the model's capability to do video editing. And finally, we basically look towards our NLP friends and borrowed this technique called back translation from machine translation, and that actually improved the model a lot more. So let's look at each of these stages in detail. The first one is single frame editing plus text to video. So this is just taking image to image, which is image editing plus text to video, and then we basically just at inference time just throw in a video and let's look at what the model can do. To our surprise, the model actually, so the thing to note here is that the model has never seen an input video. Right? It was never conditioned on input video, and this is a pure test time thing that we're trying to see over here, like what all can it do. And what we found is it actually does a pretty good job of mapping the instruction and creating at least a reasonable spatial layout to what the edit needs to be for the video. There's of course a lot more, there's a lot of artifacts. The temporal consistency is very poor, but this was already quite surprising because we found that the model is learning to copy over the edit across the video quite a bit, much more than we had expected. And the other thing is image editing data is actually much easier to get at scale. So now what you can do is you can actually expand the vocabulary of your model quite a bit by adding this image editing data. And so just by doing this simple stage training, you've converted your text to video model into an instruction-based video editing model. Of course, there's a lot more improvement that needs to be done on the video editing, but it's already getting there without actually even looking at video editing data. So in the second stage, we now want to really capitalize on the fact that this model can do some type of video editing. So to do this, we want to also condition it on input videos, because till now the model does not even know how to process an input video. So we add two types of data. The first is synthetic data, where we prompt the Llama model to create a bunch of editing instructions, and then we apply single frame edits to our video. So we'll take a large video, we'll basically take an image editing model, and we'll just apply single frame editing. Of course, these are not going to be consistent, right? Because this image editing model is just being applied per frame independently. But we found that we can sort of live with this quality for now. And the second thing we end up adding is segmentation data, which is basically where we give the model an input video, and then we ask it, we provide an instruction, hey, segment out this particular bicyclist, or segment out the pair. And then we highlight basically that pair in particular colors, and then now the model basically has input-output pairs and a segmentation instruction. And this was quite useful because this is the task where our input is a real video and our output is a real video. Whereas in the task above, which is synthetic data, our input is a real video, but our output is a synthetic video. And so basically adding this task where you actually have real videos as the target really helps sort of keep the model have targets which are coming from the natural distribution of videos. So it really helped basically improve motion consistency. And so now by doing these two stages, this is the type of stuff the model can already do. It can actually recognize basically that there are small, like in this case, remove the scissors, so it recognizes where the object is. It can go sort of paint it out, and it can still maintain a lot of visual coherence, which it could not do after stage 1. At the same time, we noticed that because we were basically just using this per frame image animation or per frame image editing, it was not really doing a very good job of sort of fast moving objects, or when you had a lot of camera changes, the model was actually not doing a very good job. So it would kind of work for these slow motion videos where the camera is static, but when the camera sort of moves on, it's not really going to do a very good job. And so this is where back translation comes in. So for back translation, what we now end up doing is we take the model that we had until stage 2, we use that to synthesize a bunch of video editing data from the model itself. So we take real videos, we apply an instruction, and then we get a generated edited video. And now, instead of using the edited video as the target, we actually use it as the input and the real video as the output. And we swap the instruction. So if the instruction was basically that you were going to add a cat, and you have the target video, we make the instruction remove a cat, and then we just swap the input and output pair. And what that again means is basically that the target is real pixels. So the model is going to really focus on real pixels as generation. So it's really again confined to the manifold of real data distributions in its target rather than synthetic pixels. And this basically helps improve a lot of issues with like saturation, like small types of artifacts, and natural motion. And this was quite important in getting that final bump in quality. And so here's basically the model before back translation and the model after back translation. So it's the original video basically has a yacht, and what we're trying to do is basically replace the yacht with a robotic dragon flying through the sky. So before back translation, the model does follow the instruction. It's trying to be precise, but basically does not understand what natural motion is. Because in the second stage, it's really only been trained on this per frame image editing data. So it does not understand, and the image editing model does not really add any motion. It does not add consistent motion. So the model essentially does not learn a whole lot of motion edits. Whereas when you swap it out, the model actually now sees that, okay, all real videos have a lot of motion, and objects in the real world actually move. And so in the back translation stage, the model actually learns how to add this motion back when it's performing these edits. And so you end up getting these videos where the model is adding objects and actually making them move as well. We also try to quantify for each stage what is the improvement that comes from it. So the multi-frame editing and like text to video, the second stage basically gives us a bump of about 39 points, and then the last stage basically gives us a bump of about 10 points in overall quality. Now, once we have this final model, we decided to benchmark it against a bunch of other methods on this benchmark called TGB+, where we asked humans to basically look at videos coming out of MovieGen Edit and the baseline, and then basically they are doing essentially an A/B test, and they're going to prefer the video that they like. So in the top row, we compare against this method called TAB, and we find that MovieGen's videos are preferred 90% of the times compared to the baseline, which is a pretty strong preference rate. And this sort of strong preference rate exists when you sort of compare it to other baselines as well. And 50% here would have been basically equal, where the model, like the edits coming from our model versus the baseline are both equally preferred. What we found beyond this is basically that the current benchmarks are actually not sufficient to capture all types of video editing that exist. So we introduced a new benchmark in the paper called MovieGen Edit. And on this, we ended up benchmarking against even stronger solutions. These are coming from industry, so like the Gen 3 video-to-video model. And we find that in this case, again, our model's edits are strongly preferred over baselines quite a bit. And Gen 3 has like 2 different variants, so we basically benchmark against both of them. And finally, coming to the precise editing property that I was talking about, where we want to add a cape and only add a cape and not change anything else about the video, we ended up just evaluating if our model is really preserving the structure of the input and output video, and asked humans to now not only pick a video that is more like realistic or like high quality, but also a video that is making the minimum amount of changes to the input video. And in this case, we see the strong benefit of using our approach, where like 98% of the time it's preferred over the baseline when you're actually looking at structurally precise edits that need to happen in the input video. And once you start playing around with these models, they sometimes surprise you quite a bit. So here is one example that we were actually quite surprised by. So basically here is the input video on the left hand side, and you ask the model to make the mirror dirty. The model makes the mirror dirty. It actually makes the wall dirty first, and then it actually makes the mirror dirty after that, and actually copies over the wall's dirty reflection into the mirror. When you also ask the model to add a beard to this person, you see that the reflection also gets a beard. And so a bunch of these things actually start coming out of the model, where it understands when it's trying to make an edit how these local edits, which is just about adding a beard to a person, which should only be changing those pixels around the person's face. But in the case that there is a mirror, it actually needs to go change those pixels as well. It actually understands how to do this. And so this was one of the reasons why when we were doing this editing task, we did not really try to distinguish a whole lot between if the edits need to happen like in a local area versus not a local area, because that definition is actually very hard to get right, and then you run into a lot of these edge cases. And so basically focusing on a very simple architecture where the model can basically produce all the pixels that it has to, and then it decides whichever pixels it wants to copy over and whichever pixels it wants to edit. That sort of makes it for a more general video editing model. Here's another example where basically now we have input video on the left, and then they're actually asking the model to change things. So like change the boxing gloves to fireballs. You see that the light that actually comes with the fireballs, actually you see that reflected out in the boxing bag. When you ask the model to change that basically to water balloon, whenever there is contact with the water balloon, there is actually some type of like bubble sort of forming out. So this is another example of the fact that even when you're making very local edits, there are so many interactions that happen between objects that you really cannot precisely predict what is going to happen. And so stronger and stronger video generation models are kind of necessary to get these types of edits right. And this actually launched into product yesterday. So if you go on to meta.ai today, you can actually upload your own videos and stylize them in basically about like 30 to 40 different styles. Or if you have the Edits app launched by Meta in the App Store, you can actually go upload your own videos and you can use Movie Edit to go stylize it out. Alright, so this brings me to the second part of my talk, which is the personalized text-to-video application for Movie where the idea basically is that we are now going to condition the model not on just text, but also on the image of a face. And now with this face image plus text, we're going to produce a video. So here's one more example. This is Angela, one of the authors on the paper. And so you basically have the image of this person, and then you basically made a text prompt. And now the point is that you're trying to insert this person into this video. And we try to retain as much of the identity of the person as possible. And of course, they might be in different lighting. Their face might move around. So there are lots of challenges when you're trying to basically introduce this person into a new video. It's also, I think, one of the sort of cool applications because people like to see themselves as vain as we are as humans. And so basically it's a very critical application for generative augmented reality for things like restyling yourself, like trying out new clothing, virtual tryouts and everything. And once again, when you try to look at video personalization versus text to video, you again run into basically the same challenges that we had with video editing. So the first thing is scale of video personalization data is also multiple orders of magnitude smaller. For text to video, it's actually much easier to go out and like collect a lot of diverse videos, go basically synthesize their training captions. But for personalized video, it's much harder again. And the second challenge basically for this face image plus text to video is that the face identity is very crucial. People don't like when they don't look like themselves in the output, right? You don't want a generic person coming out, you want your identity basically when you're giving that as output. So maintaining that is super critical for this application, which is not necessarily the case for the general text to image or text to video problem. And so as a consequence of this, again, we decided to basically add personalization as a post-training capability to the text to video model. The architecture for personalization, again, is quite simple. It's almost like the same thing that we did for editing, where the idea basically is that we have the text instructions, we have the image that we are conditioning on, all of them basically get encoded into a bunch of embeddings. You condition on those embeddings, and then you just like denoise your target video. So and we try to basically keep this quite simple. Again, the main thing comes out to how you're going to train this model, because the architecture, if you sort of have it simple, then you need to figure out how you're going to get the data. So we basically ended up creating these different training stages, where we start with the text-to-video model, and then we're going to have 3 stages, and each of them are trying to do something different. The first is basically a reference frame plus text-to-video stage, where we're generating short videos. And the main idea here is basically that we want the model to understand how to take identities in the input image and copy them over into the video. Because so far it has been a text-to-video model. In the second stage, we basically just increase that temporal length. So we just make that from 8 seconds to 16 seconds. And in the final stage, we end up basically improving the naturalness of the videos. In terms of where the data comes in, for the first 2 stages, we actually just automatically synthesize data. So we take a long video, we hold out its first frame, we crop out the person's face, and then we just use that as conditioning. Of course, this is going to be severely limiting in terms of the variation that it can give, because from a single video, the person's lighting and the person's face pose and everything might actually not be changing a whole lot. But the cool thing is basically that this data is very easy to get once you have a lot of text to video data. You can synthesize this at very large amounts of scale. And in the second stage, this is where we basically have lesser data, but now we actually go find videos of the same person, and now we just use basically the conditioning frame coming from a different video, and this really teaches the model to generalize from a full person's like image and like convert it into a different lighting setting, convert it into different poses, different hairstyles and everything. So let's look at a few applications and like try to figure out like what matters in this case. So the first thing was basically an architectural application. And this is where we were trying to figure out that when we are embedding the face and trying to condition our model on the face embedding, should we train that face embedding or should we use an off-the-shelf face embedding? And what we found is basically training that face embedding matters a whole lot. Essentially, like using off-the-shelf embeddings, the model is not able to preserve face identity, and face identity is very critical when you're trying to do this personalization application. So we are basically measuring 3 things over here, which is like how well is the identity being retained and how consistent is the face basically as you're generating the video. And what we found is basically if you freeze the embedding versus like you train the embedding, there's a huge performance difference, almost like going up to about 70 to 20 points improvement across the board. And so this basically makes it pretty clear that we should be training the embedding when you're trying to generate faces. The second was basically how important is that last stage, where you are trying to take basically frames coming from a different video, condition on the faces from that, and then generate a separate video. And it turned out that this particular stage is also quite important when it comes to like generating overall the natural motion. Because if you just condition on faces coming from the same video, the model does not understand how to generate different poses. So it just like tries to keep the face static. So if the reference image was just like a person looking at the front, the model will always basically have a copy-paste artifact where the model just generates a person looking in the front and the person can never move their thing. Whereas when you start using this cross-paired data, it actually gets very naturally a lot of pose variations, lighting variations, and so it really learns how to basically keep these things intact. The other thing that we ended up seeing quite a strong improvement for was the text alignment. So if you're trying to basically say that, hey, take this person and put them in a completely different setting. So make it a night scene, or make it a day scene, or make it a desert scene. These things typically require a whole lot of lighting changes. And so if you don't have cross-paired data, the model actually does not make these changes very well. And so this is one of the reasons that we saw text alignment go up significantly when we started using this cross-paired data. We ran a bunch of benchmarks, basically again comparing this model to ID Animator, which is the state-of-the-art method at the time. And here again, I'm comparing basically, it's a human evaluation A/B comparisons, where we're asking raters to pick generations coming out of our model versus the baseline, and we're asking them to pick this based on different types of axes. So overall quality, if the face is consistent, if the motion in the video looks natural, if the motion actually is complete, and whether the text alignment, if the model is actually following the text prompt or not. And across the board, we see basically a strong preference rate for our, or a win rate for our model. And this actually shows that a bunch of design decisions that we did actually seem to happen. And I'd like to thank all of our collaborators in MovieGen. It was a massive team effort with a lot of people working super hard. I'm just one person talking about it, but really this would not have been possible without all of these amazing people and really all of that hard work and dedication across many, many, many months. Thank you.
Okay, we are ahead of time, but maybe we can have one quick question if somebody wants to ask. Yeah, please. Yeah, you can quickly.
Yeah, just want to say thanks for the great talk. I'm just wondering, going back to the video editing section, you mentioned there's one stage where you where you make multiple image editing of the same video across the temporal dimension. I'm just wondering how much the inconsistency between each image could affect the overall video editing, and how do you deal with it?
Yeah, so it's a great point. I think it matters. So for certain operations where it's about changing color of the object, there is not a whole lot of inconsistency because image editing models are pretty good, right? So they're able to change the color, and as long as they can localize the pixels of the object, they can go change the color, and there is no inconsistency, or very limited inconsistency. But for things where it's okay, replace the yard with a dragon, that's the type of stuff where it's very hard because you don't know what scale you ended up adding the new object at, where you ended up replacing, because we never specified what type of dragon it is. Dragons also come in thousands of varieties. So which dragon ended up coming? So this is where a lot of these things cause inconsistencies. And that's basically why back translation type, the fixes that we have for back translation matter the most for these add type operations, where you're adding a new object and that object needs to be natural and move. Okay, thank you so much.
Yeah, thank you, Ishan, for a great presentation. Now we have Dan D. Goldman from Lucasfilm. So as a quick introduction, he's a principal engineer and AI ML architect at Lucasfilm, ILM, and an affiliated associate professor at the University of Washington. He previously worked at Adobe, where he developed the core technology behind Photoshop's content-aware field, and at Google, where he led computer vision research and development for Project Starline. His career spans research roles across leading creative and technology companies. Thank you.
Thank you. I have to add that I co-developed content over film with Ellie, who's giving the next talk. So I'll give credit where credit is due. So I want to start briefly with a little bit about myself. My career actually started at Lucasfilm Industrial Light and Magic in the 1990s with lighting and rendering and production. Then I took a long break from film. I went back to school for my PhD, and then I joined Adobe Research. Spent about 8.5 years there.